On this rainy day, let's start this third. So before I start what I want to speak about today, let me come back to some questions I was asked yesterday and which are relevant. So this is how to define Hastings-Levittov model, and I have described yesterday a way to do that using the so-called strike model. So there are two these are preliminary remarks. So about Hastings-Levittov model. So let's recall that for DLA, okay, DLA, you at each stage you choose a point on the boundary of the cluster you have, and you add there an object. Okay, and there was this question about maybe you cannot add such an object because maybe the place is too narrow or something. So the way to get around this thing was by using conformal mapping and just saying that, okay, we always add as an object a piece of an external array. Okay, this always exists. Okay, well, it always exists. It doesn't exist if the domain is not locally connected, but this doesn't happen here. So this was a strike model. Okay, so this is the strike model, and this model can be seen as iteration of conformal maps, which is coherent with the fact that it is modeled by Loevner differential equation, which is nothing but a theory of iteration of conformal maps. So strike model, so this is iteration of maps, like, so you map the complement of the disk to the complement of the disk minus some little piece of external array. Of course, you choose the point here at random with uniform law, and you choose the length here according to the so the length is not random, of course, but it depends on alpha. Okay, and the value of the derivative at the point you. So this is a so-called strike model, because you always, so when you iterate such a thing, so at the first step you get that, and then the next step you will add an object which will be an external array. So if the external array is somewhere here, well, you may have something like this. It's not a straight line anymore, of course, because the domain is not a circle. But then the next time you may choose an external array starting from here, so you get something like this, and then this, and then this, and then you get the picture. Okay, so this is strike model. So this strike model has some, so it's nice because it's well defined, etc. But it may have some drawbacks because it's not very physical. Okay, it's not. We would like to add something which has a surface. Okay, and that's so I will not speak about that because it's just a modification of this model. So essentially, all things are the same, but not all. Let me tell you a little bit. So this is a so-called bump model. So instead of iterating such maps, we iterate maps which looks like this. So again, you choose a point at random, but then you add a piece of. So you have to choose. You have to decide what it is exactly. Okay. So it's yeah. Okay. Thank you. So when we decide a rule to what is this, and I will not go into that. Okay. And then of course what you get is cactus-like picture. Okay. Now, at first, when I started to study this, I said, "Well, this is not important to study one or the other," but actually it is, And especially if you look at Hastings-Davidoff model with alpha small. Okay, so if you look at alpha small, so I will speak about alpha small tomorrow. Okay, today I will concentrate of estimates about alpha for alpha bigger than 1, and tomorrow I will speak about alpha less than 1. But let me just tell you a little bit about that. For alpha small, if you have the strike model, well, it looks like if you let n be very big, it looks like a brush. Okay, so you have something like this. Well, very, very, and the overall shape is about round. Okay, so in some sense, it means that well, even if this is not proven yet, okay, if it's only proven for alpha equals 0, but for alpha small, it looks like the domain is converging in the Carathéodory sense to a disk. Because all these fjords that you create have no harmonic measure. But if you take the bump model, then things are much clearer, because the bump model, the fact that you have things with area, they have a tendency to clear out, to making the fjord disappear. The fjords disappear. So actually, for the bump model, unfortunately, I had pictures of that, but I don't know where I have put them. So actually, in this case, you get really around this shape, and the fact that you go toward a circle, it's much clearer. Okay, so this was the first. So this was the first remark I wanted to make. Okay, now the second remark is about Loebner processes driven by functions. Okay, so again, we have seen yesterday that Loebner processes are I mean, it's equivalent to give a Loebner process or to give a measurable family of probability measures on the circle. Okay, so we say that the Loebner process is driven by a function when mu t for t greater than 0 is actually Dirac mass at some point lambda of t, where lambda maps 0 infinity into the circle. Okay, so the function lambda is called the driving function. So example, so we have seen yesterday that if lambda is constant, then we have just growth along a line. So when lambda is square root of kappa, well, I guess e to the I square root of kappa bt, where bt is the Brownian motion, we have SLE kappa, so radial SLE kappa. And in this case, the function lambda is continuous. So now, the fact that we have continuity of the function is not so important here. So when we have a so that's 1, that's 2, that's 3. So when we have HL of alpha, okay, then we have lambda is a step function. Okay, it's constant along intervals which are precisely the intervals tau I plus 1. Okay. Well, except that here we have not normalized. So if you normalized, it's not exactly the same intervals, but let's forget about this normalization. So actually, step functions, what are step functions? Step functions are particular cases of functions that have a limit from the left and the right at every point. Okay, and functions that have a limit from the left and from the right at every point are precisely uniform limits of step functions. Okay, so the natural class of functions here. Sorry. Well, on an interval. On an interval, it's just a uniform. No, I said uniform. So functions with a limit from the left and the right on an interval are precisely uniform limit on this interval of step functions. Okay, so on 0 infinity it would be uniform on every compact set. Okay, so this is the right class of thing because. Well, and precisely the fact discontinuities will allow this dendritic behavior. Okay. So, for instance, let's consider a very simple growth. If you have a growth like this, okay, this is a very simple growth. I mean, this is very natural growth. But the driving function here is not continuous. Okay, because when you go here, when you cross, you start at another point on the boundary, which has nothing to do. So the fact that you are precisely exactly at the same point here is irrelevant. Okay, so starting on the opposite exactly here or starting here doesn't make any difference. Okay, so the natural class is precisely the class of, well, say Cadillac functions. Okay, continuous from the right and with a limit on the left. I mean, you can always make continuity on one of the 2 points. It doesn't matter. Okay, so when we go down to random driving function, so what is the natural class of random function that we have? So of course Brownian motion is continuous, but there is a natural class of random processes which have limit from the right and the left at every point. This is the so-called Levy processes. And actually we will see, so I hope I have time to do that tomorrow. There is a connection with of Levy processes with what I'm saying about. So for instance, for alpha equals 0, HL0 is a process driven by, is a Loeffner process driven by a Levy process, which is just a compound Poisson process, so a very simple Levy process. And using that, we will be able to prove the fact that we have round shape for these things. Okay. So the Loeffner process driven by Levy processes, this has been considered a long time ago already by physicists. And so I will tell you a little bit about that tomorrow, and I will tell you more in Moscow in the conference. So for those who will come, I will speak about that there. Because, well, let me just advertise this. Actually, Loeffner introduced his theory for purposes that have nothing to do with that. He introduced this theory for proving Bieber-Bach conjecture for n equals 3. So this is about coefficients of univariant functions. So it's a purely complex analysis problem. And he was able to solve the conjecture for n equals 3 using that. And I have come back to this problem for Levy processes, and it happens that the coefficients that we obtain for Levy processes have surprising properties that I cannot explain yet, but that I will speak about then in Moscow. Okay, so that's about all I wanted to say. Are there any more questions about the material so far? Okay, so today, so what is the plan for today? I would like to speak about alpha greater than 1. So it will be the case alpha greater than 1. And to show that the growth is controlled. So we're bound on the so the first theorem will be of Carlson and Makarov. and it says that so fix delta positive and consider. Well, the delta will not be apparent in the theorem, but it will be apparent in the proof. And consider Healy-Shaw process. So this will be HS of 2. So that is the Loevner process with mu t equals epsilon t delta square, okay, delta zeta. Okay, so this was the Healy-Shaw process introduced by Carlosson and Makarov. So this is the regularization of Carlosson and Makarov. And so I recall that this epsilon is the first t for which you have the image of the conformal map. You go along here, and you go along epsilon here, so that on the image you reach for the first time distance delta to the boundary. Okay. Then there exists a constant c positive such that the diameter of kt is less than a constant times t to the power 2/3. Okay, so which is exactly Kesten's estimate for Healy-Shaw. So Kesten proved the same estimate for DLA. Okay, but for DLA it is not sharp. Okay, well, it is supposedly not sharp because the exact power law is not known, but it is supposedly not this one. But for Healy-Shaw, this is sharp. And this is sharp because, of course, I have to mention something. When I say Healy-Shaw, of course, I should also precise what is the starting point, K0. Okay? If you start with K0 equal a disk, then there is nothing to do because you always get a disk. Okay? So the thing really arises when you take K0 not being a disk, so that you have curvature, and this curvature tends to turn into these arms, dendritic arms, etc. So when you start with a segment instead of a disk, you can do the computation. You start with a segment. You can use the computation. But, by the way, this uses Chebyshev polynomials because you have the conformal maps from the outer of the disk to the outer of the segment, sending the trigonometrical basis to the Chebyshev polynomials. Okay, so and then you get exactly this. Then you get exactly this. So this is sharp. Now I will not prove completely this theorem because this is extremely deep one. This is the extremely deep theorem, and so there are technical details that I will leave on the side, but they are easy to admit, I would say, because they are kind of intuitive, even if they are not so easy to prove. And but also I will admit a lemma, which now I will now state. So, and this lemma, if I wanted to prove it, I would need another 5-hour course. This is very deep theorem. So this is. So I will not state it immediately, but it will be apparent in the sequel. Okay, so let's start the proof. So sketch of proof. Well, and later, okay, I didn't mention that, but sorry, before I start the proof, let me state a corollary of that. So it will follow by exactly the same lines. This is for alpha less than 1, alpha greater than 1, sorry. If alpha is greater than 1, and we consider HS of alpha, then we have, so this is again, then d mu t of zeta is epsilon t of delta zeta to the alpha d zeta. Okay, so this is a Loevner process with this. Then there exists C positive such that the diameter of kt is less than c times 2 to the power 2 divided by 1 plus alpha. Okay, so notice that for alpha equal 1, we get exactly t. So alpha equal 1, we will get t from the right and from the left, and we will see the phase transition that I spoke about at the beginning. Okay. Okay, so let me state another theorem, which will be the working property, actually. So theorem 2. So we will study the time needed to essentially double a size. Okay. So, or maybe not double, maybe take 10 times the size. And this goes as follows. So suppose f0 prime of infinity. So again, f0 prime of infinity, I recall that this is a logarithmic capacity. So this is comparable to the diameter. So suppose that this is 1 and t prime of infinity is 10. Okay, well then t is greater than a constant time delta to the power 3/2. Minus 3/2, sorry, of course. Okay. So let's prove that theorem 2 is greater than that theorem 2 implies theorem 1. So this is just, I mean, this is easy, but let's go into that. So theorem 2 implies theorem 1. I didn't say theorem 1 here. Well, so if this is true, so if theorem 2 is true, then time necessary to pass from size 10 to the n to size 10 to the n plus 1. Okay, so this will be greater. So we just normalize everything to apply theorem 2, so we divide the picture by 10 to the n. So this changes delta to delta divided by 10 to the n. So applying this, we get that this is greater than c times delta divided by 10 to the n to the power minus 3/2. Okay? And so this is constant time delta to the power. So delta will not play, the role played by delta is a little bizarre in this thing. And then 10 to the 3n over 2. Okay, so now time, so this implies that time needed to go from size 1 to size 10 to the n, say. Well, this is just a geometric series, so it's equivalent to the last term. So this is greater than c to delta to minus 3/2, 10 to the 3n over 2. Okay, so it means, so that now we are done. So it means that at time t less than c delta to minus 3/2, 10 to the power 3n over 2, size is less than 10 to the n. And so now changing so this is this to the power 2/3, and we get the result. Okay, so that's very easy. So it's exactly the same thing. Okay. Okay, so now let's go to proof of theorem 2. So now we have the main lemma, which is lemma 1, okay? And the main lemma says, okay, so we need to estimate these, we need to have control on the quantity epsilon t, okay? And the estimate we need is precisely the following. So there exists capital C, small c positive, such that if phi is in sigma. So sigma is the class of functions which are injective outside the unit disk and which are normalized by phi prime of infinity equal 1. Okay. So, and 0 less than delta less than 1, then integral over d delta of epsilon of zeta delta square d zeta is less than c times delta to the power 1 plus c. Okay, so let me comment on that. Let me comment on that. So, comment. And this will be Berling estimate. Suppose you have a domain, so which is contains infinity. Okay, so the outside of some cluster, and you take a point on the boundary, and you take a disk of radius r, small r. Okay, and now you look at, so you make a Brownian motion come from infinity. Okay, this Brownian motion will hit the cluster at some time. What is the probability that it hits the cluster within this circle? Okay, and how does it scale as a what is the power law? Okay, so the Berling estimate is an estimate valid for any domain, and it says that this probability is less than square root of r. Okay, this is a Berling estimate. So in other words, the harmonic measure of this ball is less than a. So omega will always mean harmonic measure at infinity. Okay, omega of disk of x r is less than c times square root of r. Okay, now using this estimate, so this implies easily that epsilon of zeta delta is always less than square root of delta. And using Berling estimate, we get here c delta.
Pardon? What's Berling estimate? What's written down there? C
times square root of r. R is the radius. This is x. Okay.
That's probably an ignorant question, but C, of course, it's not an absolute constant. It depends on.
Yes, it is actually. It is actually. Yeah. There is an absolute constant. Okay. And so this implies that the integral over delta d of epsilon square is less than delta. Okay. So this is an improvement of Berling estimate. Okay, but this is also true for any domain. Okay, so it means that, so in some sense, main lemma says that Berling estimate is true, but at some places, it must be so that at some places we have improvement of Berling estimate. Okay, Berling, so the extremal property cannot hold for any disk of radius r. That's the philosophy here. Okay. Yeah, the extremal yeah, you're right. The extremal configuration is when you have a tip. This is the basics of the, I mean, the paratonnerre. How do you call this? I don't know the English word. The thing you put on the roof for the lightnings to come on it. So these are extremals because the harmonic measure there is maximal. So it's a maximal probability that the lightning will go there. Okay. So in some sense, main lemma says that you cannot have these kind of things everywhere. There must be places where you are hidden, but in a very strong and quantitative sense, of course. So it's not easy theorem. Okay. So So the theorem 3 exactly says what I was saying now. So this is due to Carlson. And later it was improved by Carlson and Makarov. And if I have time at the end, I will speak a little bit about Carlson-Makarov works about that. Okay. So this theorem says that the maximum number of disjoint disks of radius delta and harmonic measure greater than delta to the 1 plus c over 2. So c is a positive. C is positive, okay, is less or equal to constant A times delta to the power minus gamma of C, where gamma of C is little o of 1 at 0, so it goes to 0 as C goes to 0. So now later, Carlson and Makarov improved it to gamma of C equals a constant times C, where the constant here has a lot of importance. I mean, the exact value of this constant is related to the so-called Brennan conjecture, which is a main conjecture in this field. Okay. So this is a very deep theorem, and I will not go into that. Okay, so that's this theorem precisely said what I said before, that you cannot have. So let me just show you why theorem 3 implies lemma 1. It is quite clever estimate. So theorem 3 implies lemma 1. So how much time do we have? Okay, that's good. That's good. Okay, so we cut the circle into dyadic intervals. Okay, so dyadic, you know what it means. So the circle, you may cut it in 2 half circles and 4 quarter circles, etc. So this is what I mean by dyadic intervals. Into dyadic intervals, I knew such that the maximum of epsilon of zeta in I nu is comparable to the length of I nu. Okay, so this can be done by a kind of stopping time argument. You can do that. Okay, and so this implies that the integral over delta d of epsilon square will be less or equal to the sum over nu of I nu cube. Okay, because on each interval epsilon square is I nu, so you have I nu cube coming here. Okay, so now let's zeta nu. This will be the center of I nu, let me draw a picture. So it will be at a very small scale, so the circle will look like a line, okay? So let me draw a picture with a line. So we have here I nu, this is zeta nu, and I look at the zeta nu plus I nu, I nu here, and I look at the picture by the map phi. So I have here phi of I nu, and I have the point here. This point corresponds to this point, which I will call A nu. Okay. So by construction and by the definition of epsilon, we have that the distance from phi, from A nu to d omega, so this is omega, is comparable to delta. Okay. Okay. So now, moreover, so this involves a little bit of technicality. Moreover, there exists a constant lambda such that the harmonic measure of the ball of center A nu and radius lambda delta is greater than c times I nu. Okay. So this, well, I will skip the proof of that, but it follows from classical things in complex analysis. Okay, so now, and so this is first, and second, the distance between A nu and nu prime, this is greater than a constant time delta if nu is different from nu prime. Well, this is just because if you look at the points here, zeta nu plus I nu, in the hyperbolic, the Poincaré metric of the half plane or in the complement of the disk, they are separated. The mutual distance is greater than a constant. So it means the same here. And since we can compare the hyperbolic metric and the quasi-hyperbolic metric, which is just ds divided by the distance to the boundary, we get that. Okay? So 1 and 2 imply that the balls B of A nu lambda delta are essentially disjoint. Okay, and okay, they all have the same radius. And so applying theorem 3, so we can apply theorem 3. And so the number of I nus with I nu greater than delta to the 1 plus c over 2. I nu is essentially the harmonic measure of the ball. Okay, so the number of balls here with this is less than delta to the power minus gamma of c. Okay, and now we can just compute. So we can just compute, and we get that the sum of I nu cube. So this is less than the sum for I nu greater than delta to the power 1 plus c over 2, plus the sum for I nu less than delta to the 1 plus c over 2. Okay, and this is less than so we have this number here is delta to the power minus 3 is minus gamma of c. And each of them, each I nu, we use for each I nu, we just use Berling's estimate. So we have delta to the power 3/2. And for those which are less than delta to the power 1 plus c over 2, so we have I nu cube. So we just keep one I nu and take I nu square. So I nu square is less than delta to the power 1 plus c. And then we have I nu. But then we use the fact that the I nus are disjoint and the sum is less than 1. Okay? And so we get delta to the power 3/2 minus gamma of c plus delta to the 1 plus c. Okay? And this is less. So there are constant over there. Okay? So this is less than a constant time delta to the power 1 plus c if 3/2 minus gamma of c is less than 1 plus c, which is possible if c is small enough. Wait a minute. No, wait a minute. So greater, because we have a delta. Delta is less than 1, which is okay because then we need. This is equivalent to gamma of c plus c less than 1/2, and this is possible if c is small enough. Actually, we don't even need that. We need much less than that. Okay. So at this point, we already get an estimate for the size of the cluster. So let's make it as a remark. Because this is important to understand this business. So at this point, we can prove that diameter of KT is less than a constant time t to the power 1 over 1 plus c. Which is already something, okay? Because this is less than 1. Okay, so it's less than ballistic growth. And but first of all, we know that we cannot take c equals 1/2. If we could take c equal 1/2, then it's okay. But this shows that we cannot. And so we need to, and furthermore, we don't know what is c. So we don't know what. In fact, maybe c is very, very small, and so we get no control. So the beauty of the proof by Carlsson-Makarov is to use the existence of this c, which is kind of very qualitative in some sense, to get an exact estimate. So let me just show you how to prove that, because that is the idea we will use to get the other tomorrow the estimates from below. Okay, so we just use the fact that diameter of KT is equivalent to C of t, and we get estimate on C of t. Okay, and so I recall that we have the equation C dot of t equals norm of mu t C of t. Okay, and theorem 3, well, lemma 1, more precisely, lemma 1 implies that norm of mu of t is less than delta over C of t to the power 1 plus c. Because again, we have to normalize things in order to apply lemma 1, which was a lemma for functions in sigma, so that phi prime infinity equal 1. Okay? So we get that C dot of t is less than, sorry, there are too many c's, but this c has nothing to do with this one. Delta to the power 1 plus c, C of t to the power minus c. So it's ugly, I confess, but okay. So C dot of c c of t to the c is less than delta to the power 1 plus c, and then we can integrate, and we get the estimate. Okay, so that's actually the way we would like things to work, because we have this. We know that this quantity c of t is equivalent to the diameter, and we have an equation for c of t. We would like this to work, but it does not work. That's a funny thing. So the proof that we will use now doesn't use c of t, and it's actually an open problem to have exact estimates for the derivative of c of t. And another thing, this estimate is the only one we can get for DLA using this method. Or for HL alpha, for Hastings-Levitt over the alpha, we get also an estimate here with an alpha somewhere. I don't remember exactly where. Okay, and that's the only thing we can get. That means that the result for Healy-Shaw doesn't translate to Hastings-Levitt. This is also another open problem: how to get estimates for DLA and for Hastings-Levitt for the random process. Okay, so this is for the remark. Okay, so in order to prove the theorem 2, as I said, we will not use c of t. Instead, we will use the quantity so r of t. So that will be the maximum of ft of zeta in delta d delta. Okay, so this is of course this is comparable to the diameter, no doubt. But we will use the fact that precisely we are at the tip, that there is no points further. We will use some geometry linked to the fact that we have here the maximum. And so we must prove that if R0 is comparable to 1 and R of t is comparable to 10, then t is greater than c delta to the power minus 3/2. Okay? So let me draw a picture. Let me draw a picture. So we have here, say we have ks. Let's take s less than t, less than capital T, greater than 0. Okay? So here we have ks, here we have a point 0, say 0 is here, and here we have kt. Okay, and here we have the point, precisely the point at maximum distance. Okay, so now we will. So this is r of t. Okay, and we'll go a little bit further at delta here, and we choose the point A here. So that will be the point A. Okay, so we draw the line between the points which attain the maximum and 0, and go further by delta. Okay, and yes. Now suppose that r of t minus r of s is greater than 10 delta. Okay. Now we draw the circle of center A and radius 10 delta. Okay, so let's say, well, the picture is wrong, but that this will be 10 delta. And since we have assumed that we have this circle does not hit ks. Okay? And so we let t0 be the first time we hit the disk BA of 10 delta. Okay, so let me draw a black, or maybe a red cluster here, so we have, well, something like this. So here we have KT0. The first time that it hits the circle here. Okay? So now I claim, it is sufficient to prove that t minus t0 is greater than delta to the power minus 1/2. Okay, because to reach size 10, we must do 1 over delta times this thing. So 1 over delta times delta to the power minus 1/2 is exactly 1 over delta to the power 3/2. Okay, so this is clear. Okay, so is it? So we must prove that. Okay. And now we use some analysis linked to the Loevner equation. So we write z of x equals fx minus 1 of a. So we pull back a using the Loevner flow. Okay. For t0 less than x less than a. Okay, and we put y of x equals modulus of z of x minus 1, which is, by the way, equivalent to log of z of x, since well, I just point this out because this will be linked with the Green's function. Okay, now the z dot of x divided by z of x, this is by Loevner equation, integral from z of x plus zeta divided by z of x minus zeta d mu x of zeta. Okay, this is just Loevner equation. And so taking real part, we get that y dot of x divided by y of x will be, so minus, I put the minus sign here, will be about integral of d mu x of zeta divided by z of x minus zeta square. You just take the real part of this and you obtain that. Okay. And now we have lemma 2. I didn't have a lemma 2 yet, did I? Okay. So lemma 2 says precisely that integral of d mu x of zeta divided by z of x minus zeta square is less than a constant times square root of delta. And then we get the square root here, which will be the right thing. Okay. So I wonder how many details I can. Yeah. Okay. So let me give a rather detailed proof of that, because this is crucial. This is the heart of the matter. Okay. So proof. So we can assume, without loss of generality, that z of x is just 1 plus y. Okay, so that means that it's precisely what happens here. So it's the maximum is attained at the point 1 on the circle. Okay, that's what it says. And so y is comparable to epsilon of 1. Okay, so the function epsilon at point 1. Okay, and now we are going to localize. What we are going to do is precisely localize the main lemma. So in order to do that, we so for 0 less than n less than log y, we just put yn equals 2 to the n y, and in. So this So this is not the interval, but it's y minus yn 1 plus yn. So this is not the interval, of course. So the picture is the following. So you have here 1. So you have here y. So here you have yn. So you just look at the interval centered at 1, the interval of the circle, which size essentially yn. Okay? So we just do these little things. It's a way of localizing here. Okay? And then integral over d delta of d mu x of zeta divided by z of x minus zeta square will be the integral over I naught plus the sum of the integrals over I n plus 1 minus I n. Okay? And on each of these intervals, the denominator is very well controlled. Okay? So what we get is that this is less than the sum of y over yn square, because the control I mentioned is just 1 over yn square. Okay? And then integral over in of epsilon square. Okay? So that's the way, that's the thing we obtain. And now what we need is to have a local estimate here. Okay, we call that the main lemma says that the integral over the circle of epsilon square is less than delta to the power 1 plus c. Now we need a local version of that. Okay, and so now I will admit two things. So now let's put Rn equals 1 plus yn. So this is the point. So this is 1 plus yn. Okay, so this is Rn. Let's put dn equals yn phi prime of Rn, which is the same as the distance of phi of Rn to d omega. And recall that d0 is equivalent to delta. Okay. Then, what I claim two things. So we will admit that 1, we have that phi prime of y plus 1 is less than a constant times phi prime of Rn. I will explain why this is true. And second, and this is precisely the localization I mentioned, this is less than yn to the cube delta over dn to the power 1 plus c. So why is this true? So this is true precisely because we have taken the point which is at maximum distance. So it means that at this point you can draw a cone inside the domain. Obviously you can draw a line. Okay? And the fact that you can draw a line means that the geometry there is well controlled. Okay? And this control precisely says that. So it's in some sense it is not so, I mean, it is not very hard to admit this, okay? That we have this phi prime of Rn should go rather fast to infinity, and this this must be true. Now, how to obtain this? So this is just localizing the main lemma. So this is now a very, I mean, very tedious but very elementary thing by just localizing the conformal mapping. Okay, and you get that, but it takes a few pages. Okay, but there is nothing deep there. Okay, so now we can finish because we have that integral of d mu x over z of x minus zeta square. So this is less than the sum of y over n square integral over in of epsilon square, as I said. Using the two estimates here, well, actually using the second one, we get that this is sum of yn delta over dn to the power 1 plus c. Okay, And now we take the power 1 here, so we get that yn delta over dn. So using 1 and 2, this will be less than constant time y. Okay, and so this will be less than c times y, sum of delta to the dn to the power c. Okay, and what we have here is precisely a geometric series with a ratio less than 1. Okay, so this is finite, and this is less, and y is less than square root of delta by Berling estimate. And we get the result. Okay? So now, maybe I will skip the proof of this last thing. So let me just show why lemma 2 implies the theorem. So lemma 2 implies the theorem. So this is just a comparison of Green's function. So you put G1, so this will be Green's function for, oh, I shouldn't have erased, okay. For omega t, and G0, this will be Green's function for omega 0. Omega t0, sorry. Okay. Now, by maximum principle, G0 is greater than G1. Okay, and now a very short analysis that I need to skip, unfortunately, because I have no time. Show that actually we get better. So a short analysis using no more than Arnak's inequality. Okay, shows that there exists epsilon positive such that G0 is greater than 1 plus epsilon G1. Okay, so this is not very deep, and now we are done, because now we can say that this implies that if you look at log of y0 divided by y1, so we come back to here. Okay, so we have the log of y0 divided by y1. This is greater than a constant c because of that. Okay, because of that, and this is less or equal to the integral from t0 to t of minus y dot divided by y. And now the estimate here, we plug it in here. So this is less than the integral from t0 to t of the integral for d mu x of zeta divided by z of x minus zeta square dt. And this is less by what we have just seen by square root of delta. So this is less than a constant times square root of delta t minus t0, and we get the result. We get that t minus t0 is greater than a constant divided by square root of delta. Okay, and this gives the proof. So this is this was tough, I would say, and I haven't proved the main ingredient here, which is of course this estimate of number of balls. Okay, so to finish with, let me just show you how it implies how we can apply this to HL alpha. So this will be no more than just an application of Hölder's inequality. So proof of corollary. So So the focus will be on the main lemma. The rest of the proof will be exactly the same. So we need just to change the estimate of the main lemma, this integral of d mu x of zeta divided by z of x minus zeta square. So what we get here is integral of d mu s of zeta divided by z of s minus zeta square. So this is less, so I mimic what I have written there. Sum from n greater than 0 of yn, 1 over yn square, integral over in, and then I have epsilon to the alpha, okay? Because I am with the Hastings-Levitov, Hilly-Shaw alpha, okay? So the d mu is epsilon to the alpha d zeta, okay? And now I use Hölder. So this means that 1 over in, integral over in of epsilon to the alpha to the power 1 over alpha is less, well, the LP norm are increasing, that's what I use. So this is less than 1 over in, integral over in of epsilon square to the power 1/2. Okay, so integral over in of epsilon to the alpha is less than in to the power 1 minus alpha over 2, integral over in of epsilon square to the power alpha over 2. Okay? So the sum will be less than the sum for n greater than 0 of 1 over yn to the power 1 plus alpha over 2 sorry, what did I write here? Yes, and then the estimate for epsilon square. So this is yn cube delta over dn to the power 1 plus c to the power alpha over 2. Well, that's what we get. I mean, it's just Hölder inequality. I must confess that I forgot how to get from, but it's very easy manipulations. Okay, and so this is sum for n greater 0 to yn to the power alpha minus 1, and then I have delta over dn to the power alpha 1 plus c over 2. Okay, and now I want to take some of these here, so with the same power as yn. So I want to take alpha minus 1 out of this. Okay, but this alpha minus 1 must be less than, so I must check that alpha 1 plus c over 2 is greater than alpha minus 1, which is clear because c is positive. Okay, and once you have this, so you get sum for n greater or equal to 0, yn delta to the dn to the power alpha minus 1. Okay, I use strongly the fact that alpha is greater than 1 here. So the estimate, I first said, okay, this is impossible because it is true for any alpha, but not. I use the fact that alpha is greater than 1 because, for instance, these inequalities, I use these inequalities. And these inequalities becomes wrong if alpha is less than 1. So the fact that alpha is greater than 1 here is crucial. And then here you have delta over dn to the power alpha 1 plus c over 2 minus alpha minus 1, which is a constant which is totally irrelevant. The only thing you need is that it is positive, okay, so that you get a geometric series here. And so you get this, and this gives precisely constant time delta to the alpha minus 1 over 2. Okay, and now from this, it is easy to see the estimate 2 divided by 1 plus alpha. Okay, so this is just, I don't claim a lot of things here. This is just deep Carlson-Makarov stuff plus Hölder inequality. That's it. Okay. Okay, so I think I will stop here for today. So tomorrow I will prove that for alpha less than 1, the diameter grows at least as t to the power 1 over alpha. And so I will need first to make a small detour through integral means of univalent functions and this theory. And by the way, I can speak about, because this is also the Carlson-Makarov stuff is related to that too, so I will speak about that.